Okay, thank you. I've just turned on the recording, so yeah. So we're going to be doubly make sure we check everything's okay. Before we start with this session, I thought I'm having quite a few questions regarding the question 3 on the assignment. So I'm just going to bring that up. I'm going to share my screen and bring up question 3. Right, so bear with me. I'm just going to bring up the PDF. Okay, so can you all see the? Oh, hang on. Have I got? Yes. Can you all see the cover sheet? I'll scroll down to question 3. Right. So question 3A part 1. So essentially, what this is using a similar code to. Somebody got the icon? It is using a similar code to one from the notes. Okay, so actually, I'll share the code which I mean. So that's 2.4 from the lecture notes. So if I just share the actual screen, which will be useful for you. Okay, so it's the question asks you to derive a fourth. Here we are. So this is example 2.4 on page 18. So the question in the assignment asks you to derive a fourth order explicit Runge-Kutta method. Okay, so with the one in the notes, this these values for C, the ones you're given. Okay, so this code here will allow you to determine or allow you to calculate what the solution is for our A, B, and C values. Now, the one in the assignment has different given values. Okay, it uses the same 11 order conditions, but I will say, but you don't need all of these. Okay, that's all I'm going to say on that matter. So if you were just to copy and paste this code in, change these values up here, you probably already found out by now, but it doesn't give you a solution. That's to do with MATLAB solver routine. So this thing here can be a bit tricky, it can be a bit finicky. Okay, so all I would say is look at the number of unknowns we have got to determine and look at these order conditions. You might not need all of them. So that's all I'm going to say on that. That's a bit of a tip. Okay, so yeah, so what I thought we'd do is in this session is last week we looked at the boundary value problems, and we looked at the shooting method. Yeah, Poser, yeah, I recommend you use MATLAB. So that's for the question in the assignment. You don't have to use MATLAB. You could use any other software package available to you for solving systems of equations. I don't mind. I just use MATLAB in this case because that's what we've been using. But if you have other packages, there's Maple, there's Wolfram, there's Mathematica, there's Python, any package, Sage. If you're used to using that, with maybe you use that in the past with Killian. Okay, so all we need to ensure is that these order conditions are satisfied for your values of A, B, and C. Okay, there is MATLAB solver routine. It's tricky actually to for a computer to actually do symbolic solution. That's why things like Mathematica are quite expensive. But you know, yeah, I'd advise you to use a package because it just makes things a lot easier. Okay, so what I thought we'd do is have a look at the solution of boundary value problems. Okay, so we looked at the shooting method. That's just a straightforward application of one of our ODE solvers. You guess what the initial condition is for Y2, and you keep guessing until you get the right-hand boundary correct. One thing I thought we'd look at here is this question 4. And there's another method for solving boundary value problems called the finite difference method. Okay, so finite difference method, I'm going to have a look at that solving this boundary value problem. Okay, so what I'm going to do is I'm actually going to share my whole screen. That makes things a lot easier. Just hope, yeah. Okay, so you can see my whole screen, and there it is. Just mislaid my stylus. So bring in the question. Okay, so what I'm going to do is have a look at this question 4. Calculate the solution for the boundary value problem in question 2. Okay, so the boundary value problem in question 2 is y double dash is equal, and I've forgotten it already, 2t. So y double dash is equal to 2t as our ODE. The domain is 0 to 2. Our initial value for y is 1, and our final value for y in that domain is equal to 3. So those are our boundary values. Okay, so we know that when t is 0, y is 1, and when t is 2, y is equal to 3. So how do we solve this using finite differences? Now, what we do is we replace y double dash with an approximation, which is called the symmetric difference. Now, these are derived from the Taylor series. The actual derivations really are not really within the scope of this course. It's not too difficult. Those of you who go on to do the numerical methods for PDE's course will be doing lots of these, but for our intents and purposes, we can just sort of apply them. Okay, so here we got, this is an approximation. It's called a symmetric difference, and this is an approximation of y double dash. Okay, so what we can do is I'm going to rewrite our ODE using this symmetric difference. Okay, so we've got yi minus 1 minus 2yi plus yi plus 1 all over h squared. And that's equal to 2 times t. And I'm going to put ti. Okay, the reason being is essentially we have a number line. Actually, tn, I'm going to put. So we have a number line. This is y. So along a number line, we have what we call nodes. Okay, and these offer various values of t. So actually, that instead of y, I should really put that as t. Okay, let's just make that correct. Okay, so that's our number line, that's our domain of t, and these are the values of y for different values of t. Okay, so what we have here is this is an algebraic expression, so I can simplify it by multiplying both sides by h squared. So that'll be 2ht. Say ti. Actually, that should be ti. I've used tn because in other applications you tend to use tn. Okay, so we have what is a classic, what we call a tridiagonal system, and the reason it's tridiagonal is because of this use of the symmetric difference. Now, in this question, we're asked to use a step length of h equals 0.5. So if I was to write out this system, okay, so with h equals 0.5, we know that t are going to have values 0, 0.5, 1, 1.5, and 2. So that's on my domain using a h of 0.5. So you can see we have 3 values for which we need to solve for. Okay, so if y0, we know what that solution is, because that's y0. So solution at t equals 0 is 1, and we know what that is. So that's going to be 0, 1, 2, 3, 4. So that's going to be y4. And that solution is 3. So this is going to be y1, y2, and y3. Okay, so for y1, so when I is equal to 1, I've got y0 minus 2y1 plus y2 is equal to 2 times 0.5, actually, I'll write it as 2h. It's 2h times t. And at the moment, t would be 0.5. Okay, so that's ti, and so that would be t1, so that'll be 0.5, but I'll just put t1 for now. So that's when I equals 1 and I equals 2, y1 minus 2y2 plus y3. So you can see all I've done is added 1 to those subscripts. And when I is 3, we have y2 minus 2y3 plus y4. Okay. Yep. Okay. Thanks, Alicia. Yeah. Yeah. Okay. So multiply throughout by h squared. Yep. Oh, that should be h squared. Okay. So we have a system. Here we have the system. We have 1, 2, 3, 4, 5 unknowns and 3 equations. But do we have 5 unknowns? Because we know what that value is, and we know what that value is. Okay. So what we can do is, this is going to be y0, so that's going to be 1, but we know what that value is, so I'm going to rewrite that as minus 2y1 plus y2 is equal to 2h squared t1 minus y0, because that's known. Second one is just the same, so let's see, 2h squared t2. And the third one, got minus 2y3. Oh, sorry, getting carried away there. It's y2 minus 2y3, but I'm going to subtract y4 from both sides. So we get 2h squared t3 minus y4. Okay, so just going to move that out the way a bit. Okay, so we can write this as a matrix equation. So y1, y2, and y3 are unknowns. On the right hand side we have this vector 2h squared t2. All these values are known to us, by the way. t3 minus y4. And here are coefficient values 2y1 plus y2 plus 0y3. We've got 1y1 minus 2y2 plus 1y3. I've got 0y1, 1y2 and minus 2y3. Okay, so to solve this, it's only a 3 by 3, so we could invert the matrix. So we can invert our matrix and just bringing up. Okay, so yeah, so we can invert the matrix, and so what I'm doing off the screen is just bringing up the my solutions just so you can see the inverse. Okay, right. So where was I? Okay, so we can invert the matrix. So I'm just going to clear that screen now, and just to remind ourselves what the equation was minus 2, 1, 0, 1 minus 2, 1, 0, 1 minus 2, y1, y2, y3. That was 2h squared t1 minus y0, 2h squared t2, and 2h squared t3 minus y4. Okay, well, our known values. Okay, so remember h was 0.5. We had a vector of t array, t vector, which is 0 and in steps of 0.5. Okay, we had y0 was 1 and y4, if I remember correctly, y4 was, I'm looking this up off screen now, so that's hence why I can't see where's my y2 was 3. Okay, sorry, yeah, so y4 was 3. Okay, so if I do that calculation, too many windows, we have minus 0.99. So if I do that calculation at 0.99, 0.02, oops, and minus 2.97. Right. So inverse of A, actually it's small enough to calculate using by hand. So remember inverse of A, remember from the first year with the adjoint determinant formula. So determinant of A, what we got? So if we expand out across minus 2, 1, 1, minus 2, minus 1, 1, 0, minus 2. So what we got? We got 4 minus 1 is 3, so that's 6 minus 2 is that should be minus 6, and it plus 2 is minus 4. Adjoint of A. Okay, I always do this in 2 steps. So the first step, what I do is I calculate the cofactors, and then I transpose it. So what's that? So that's 4 minus 1 is 3. What we got here? We got minus 2 because it's the row plus the column is odd. We change the sign to a negative. What we've got? We've got 1. We got minus 2, but again it's negative, so that's 2. 4, and we've got minus 2 times 1, so that's going to be minus 2, but change the sign of 2. We got 1 minus 2, so that's going to be plus 2, and we have 4 minus 1 is 3, and that's transpose. I always forget, you know, I always seem to forget to do the transpose. So transpose that, we have 3, 2, 1, minus 2, 4, 2, and 1, 2, 3. So therefore, our inverse is minus 1/4 times the adjoint. So our solution will be inverse A times B, because if we say that's A, that's our Y, and that's our B. Okay, so it'll be multiplying those together. And that's multiplied by our constant matrix. Okay, minus 2.97. Oop, 7. Okay, if you do the sums, we get 1.475, 1.96, and 2.465. So those are the solutions to y1, y2, and y3. So the solution vector y for the whole of it, that's going to include our boundary values. So we'll have 1. Okay, then we'll have y1, 1.96 and 2.465. So those are the ones we calculated, and the other boundary is 3. So that's the solution using finite differences. Notice we had to solve a linear system. Now this had a fairly large step length of 0.5. Usually you'll have a lot smaller step length. So for example, you might have 10 by 10 or 100 by 100. And in those cases, you wouldn't use the inverse to solve the linear system. We'd use something like Gaussian elimination, or the actual topics for this week in my part of the ODEs is solving linear systems using direct methods. So I've introduced you to 3 main direct methods for solving this type of linear system. Okay, so if I just put Moodle back on, in the week 4 of Moodle, if you scroll down to my part, just zoom in a little bit for you. Okay, I've actually got the solutions to week 3 tutorial exercises. So that's boundary value problems.mlx. I'm just going to bring that in across. Okay, so you can see all of that working out. If I zoom in for you, okay, you can see that working out. Oh, where my mouse likes to go a bit too quick. Oh yes, a bit further down, and you can see all the solutions to the other questions there. Okay, and I've also got it says write a MATLAB program to calculate the solution using a shooting method and what we've just done using finite difference method, and you can see you can compare the two here. Okay, right, so that's kind of clearing up a little bit from last week. Right. Yeah. Okay, so that's the finite difference method for solving boundary value problems. You also got the shooting method. Are there any questions about the finite difference method? Okay, so it's fairly simple. It's you will end up with a linear system, and then it's just however you want to solve that linear system. So talking about linear systems, this is sort of preempting something for this week. Okay, so for my part of the unit this week, the subject is all about using solving linear systems. Now these pop up a lot. We've just seen how they pop up in finite difference method, but they also pop up in using implicit methods. So quite often we need to solve a linear system. There are a number of different methods to doing that. Okay, so in the video lectures for this week, there's lectures on LU decomposition, which is one of the most widely used methods. Something called QR decomposition, and Cholesky's missing. Okay, I'll add that. Yeah, for some reason the Cholesky, what we call Cholesky decomposition, is also there. So I've done a video for that. So that's the subject for this week's ODEs for my part. Now notice in the assignment I haven't asked any questions on solving linear systems, so it's kind of, it doesn't take too much sort of working out to realise there's going to be a question on linear systems in the exam, and you'll take the exam in the week following the end of this teaching block. Okay, so a little bit of I don't mind giving that away. That's not giving too much away. Okay, are there any questions regarding that? Okay, out of interest, put your hand up or something in the chat. How many people have sort of watched the videos, the LU factorization video for this week? If you have, I mean, I could go through an example. If you haven't, I could still go through an example, I suppose. Okay, yep, why not? Okay, well, I'll go through an example of LU. What we call LU decomposition, and I'll do a little mini lecture on it as well. What colour do I want? I want that colour. So, right, okay, so LU decomposition. Okay, so quite often we have a linear system, and our linear systems of the form AX equals B. A is what we call a coefficient matrix, X is our vector of unknowns, and B is our constant vector. So what LU factorization or LU decomposition seeks to do is we rewrite a matrix A into the product of two matrices. Okay, L is a lower triangular matrix, U is an upper triangular matrix. Okay, in the video lectures and in the notes I go through, if I find which window I'm oh, no, not that program, just too many windows open. Oops. Where's my Yeah. Okay. So in the notes on LU decomposition, I go through the derivation of formula which we use. So I'm going to be using this here. Okay. So if you want to have a look at where these come from, okay, this is the formula I'm going to use. Okay. And I'm going to make up a new example. Okay. So the example I'm going to make up, and this is totally off the top of my head. It's not special at all. I'm going to give myself some values. 3 minus 1, 2, 2, 1, 1. Okay, I just made them up because you notice they're quite small, so I don't want to make life too difficult to myself. So that's I'm going to seek to find two matrices L and U, which when multiplied together they give me A. Now LU factorization. This is from the notes. U, ij, these are our elements of our upper triangular matrix U. Okay, and we calculate them using this equation. Okay, Lik Ukj. You might notice I tend to write L's like this. This is just to distinguish it from a 1. It's very easy to get to confuse 1 and a lowercase l. So if you're wondering, why that's like that, that's why. Okay, and Lij, U that's Ujj, and that's multiplied by Aij minus a sum. K goes from 1 to L minus 1. Oh, sorry, J minus 1. L I K U K J. Okay. Also, on the main diagonal of L, we have a value of 1. So these are sort of given to you in the notes. That's on page. In the notes, if I find what page it is, it's 81. Page 81. Okay. So how we calculate our LU factorization for this is we go down the columns. So I'm going to start with column 1. So that's J equals 1. Okay, and I apply these. So U11 is equal to A11 minus this summation. So this summation goes from K equals 1 to I minus 1. Well, I is already 1, so I minus 1 is 0. So we don't have any 0 elements in matrix notation, so that's just A11. So U11 is simply A11. So that's this element here. If I go down to this element here, this is in the lower triangular region. So this, I'm going to calculate L21. Okay, so L21, according to this equation, is 1 over U11, because J is 1, multiplied by A21. Okay, note this summation, we don't use this because J is equal to 1, and therefore that K goes from 1 to 0, so this summation doesn't exist at the moment. So U11 was 1, A21 is 3, so L21 is just 3. L31 is 1 over U11, because J is still 1, multiplied by A31. And again, we don't use that summation yet because J is 1. So that's going to be 1 over 1 times 2. So that equals 2. Okay, so it's actually the same as those values so far. Moving to the second column. So this is moving to this column. So that's the J equals 2 column. We start off again. So U12, because this element is in the upper triangular region of this matrix A. Okay, and we're using this. Now we are going to have some summation terms. So we have A12 minus L, well, I is 1, but and K is 1. Oh, sorry. Yeah, I is 1, K is 1, so that's L11, multiplied by U, K is 1, and J is 2. Okay, so Lik, UKJ. So K is 1, I is 1, and J is 2. Now L11 is a main diagonal element of L, which we assume to be 1. Okay, so this is equal to A12, which is 0, minus U12. Oh, sorry, U. Oh, my apologies. Sorry. Yeah. So this summation here shouldn't be entered into yet. So I got a bit muddled up. So I is still 1. So this summation shouldn't be entered into yet. Sorry about that. Wonder what was happening. We were trying to calculate U12 with itself. Okay, so that's just A12. So that's 0. This element here, this is what we consider this to be in the upper triangular region. So I'm going to calculate U22. Now this is where I have that summation come in. So we have minus L21 U12. So I is 2, K is 1, and NJ is 2. So A22 is minus 1, minus L21, which we calculated before to be 3, and U12 is going to be 0. So that's 0. So that's minus 1. Yeah, unfortunately, I've chosen some values where they're not actually changing, but I'll continue. L32. Okay, so this is where I'm now going to be using the Lij equation. So it's 1 over U22 A32 minus L31 U12. Okay, so I was 3, K is 1, and J is 2. So that's 1 over minus 1, because that's what U22 was, times A32, so 32 is 1, minus L31, which we calculated to be 2, multiplied by U12, and U12 was 0. Okay, so L32 is minus 1. So this is the first one where we've actually got a different value. Okay, so J equals 3 is our third and final column. So that's J equals 3. So these are all going to be upper triangular elements. So these are all going to be used. So U13 is equal to A13, which is 2. U23, so I'm using this one, is equal to A23 minus L21 U13. So A23 was 2, L21 is 3, and U13 was 2. So that's going to be minus 4. And finally, U33 is equal to A33 minus L31 U13. So in this summation here, K goes from 1 to 2. So we've got another term, which is L32 U23. Okay, so A33 was 1, L31 was 2, U13, which was 2, minus L32, which is minus 1, so I'm going to change that sign to be positive, and that's times U23, which is minus 4. Oh, I shouldn't have changed it to positive because it's gone back to negative. Okay, so that'll be 1 minus 4 minus 4, so that's minus 7. Okay, so we completed all 3 columns of A. So what we can say is L. Now L is going to be a 3 by 3 matrix. We always assume that 1's on the main diagonal of L. L21 was 3, L31 was 2, and L32 was minus 1. So that's our lower triangular matrix, and U, which is our upper triangular matrix, was 1, 0, 2. The triangular element is going to be 0. U22 was minus 1. U23 was minus 4. And U33 was minus 7. And we can check that L, A should equal L times U. Okay, so if you multiply those together, you should get back to A. Now, so that's LU decomposition. Trying to find, where's my teams? Right. So that's LU decomposition. You might think, well, that was nice, John. Just did a load of working out to get two matrices. What's the point in that? I'll show you. So the reason we use LU decomposition is for solving our linear systems. Okay, so remember we're trying to solve AX equals B. So if we can rewrite our matrix A as the product of our two matrices L and U, we have this system. Now what I'm going to do is I'm going to say let Y be a vector. I'm going to say let Y equals U times X. So what that gives is I'll have Ly equals B. Okay, so an L, so that's going to look something like this. So I'm going to have, let's say if it's a 3 by 3, I'm going to have L2, 1, L3, 1, L3, 2, multiplied by some unknown, which we're trying to work out. So this is for a 3 by 3. If it's a 4 by 4, this will obviously be bigger. B1, B2, B3. Now we can work out these through forward substitution because 1y1 equals b1, so we know what the value of y1 is. Then once we've got the value of y1, we have L21 times y1 plus y2 equals b2, so we can work out what the value of y2 is, and so on and so forth. So we calculate our values of y using forward substitution, and then so that's our first step. Our second step is to solve this. So we've got ux equals y. So what we'd have is u11, u12, u13. So we'd have an upper triangular matrix multiplied by our x values. Now these x values are what we're trying to solve for in the first place. And that will equal our y values, which we just calculated and the first step, and we can calculate them using back substitution. So for x3, we simply divide whatever y3 is by whatever u33 is. For x2, we know what x3 is, so we can calculate that. And going back up through the system, we can calculate all of our x values. Okay, so, and this is a method called Kraut's method. So using LU factorization, okay. So it is actually a form of Gaussian elimination. It's a roundabout form of Gaussian elimination. But what's the beauty of this is usually what happens is our coefficient matrices tend to stay the same, but our right-hand side vectors tend to change. Now, if you're using Gaussian elimination, every time but our right-hand side vector B was changed, we'd have to do this all over again, all those row operations. But with LU factorization, we can calculate the Kraut's method. If B changes, it doesn't matter. We just go through Kraut's method again. Okay, so does that make sense? Okay, would you like, shall I, I'll go through an example of using Kraut's method. Is it, I take it everything's okay? Can you see what I'm doing, and does it all make sense? Okay, I'm going to do a very, very simple, let's say a 2 by 2 solution. Okay, so I'm going to give it a bit more bigger values because, you know, why not? And let's say x is going to be 3 and x1's 3 and x2 is 2. So I'd have 9 plus 8, so that'll be 17 on the right hand side. And I have 6 plus 10, so that's 16. Okay, so I kind of know that x1 is going to be 3 and x2 is going to be 2, but let's solve this using LU factorization. So again, so u11, so I'm doing the LU factorization on a 2 by 2, so that's going to be a11, so that's going to be 3. Oh yeah, so can you slow down for a bit? What I would say is I am going to make this recording, I am going to make it available via Moodle, so that when it's available via Moodle, you can then sort of scrabble between them, but I will try and slow down. Sorry about that. Do you want me to go back to the previous slide for a bit, or previous page? Yeah, okay, that's what the previous page is. So Yeah, sorry about if I am going a bit fast. But, yeah, so as I mentioned, this will be available via Moodle. Okay. Right, so, and then we got just one lower triangular element, so that's going to be 1 over u11 times a21. So that's going to be 1/3 times 2, which is 2/3. Okay, so when j equals 2, u12 is just going to be equal to a12. So that's going to be equal to 4, and u22 is going to be equal to a12 minus L21 u12. So a12 is, sorry, a22 that should be. So a22 is 5 minus L21, which was 2/3, times u12, which is 4. So it's 5 minus 4 over 3. So that's 50, so that's 11 over 3. Okay, so our LU factorization for this problem is 2/3, and u is 3, 4, 0, 11 over 3. I'm just going to double check that 11 over 3. So what we got 15 over 3 minus, yeah, good job I checked it. So 15 over 3 minus 8 over 3. That should be 7 over 3. Okay, ignore that. It should be 7 over 3. Good job I checked. Of course, we could always check whether we got that correctly. If we multiply these two together, we should get A. So we've got 1 times 3, which is 3. 1 times 4, which is 4. 3 times 2/3, so that would be 2, plus 0 is 2. And we have 4 times 2/3, which is 8 over 3, plus, sorry, that should be 7 over 3, shouldn't it? Okay, so we have 8 over 3 plus 7 over 3, which is 15 over 3, which is 5. So you can see that's L times U equals A. Okay, so that's showing that our LU factorization does work. So to solve, okay, so we need to solve, or part, so I don't know why I've gone to part 2. Part 1 is solving uy equals b. Oh, sorry, ly equals b. So L times y equals b, so 17 and 16. This is quite easy. So y1 is just going to be 17. y2 is going to be 16 minus 2/3 times 17. So that's going to be 16 minus 2/3 times 17. Okay, I'm regretting that now. So I'm reaching for my calculator off screen. 16 minus 2 over 3 times 17. That is 14 over 3. Okay, so we've got our y1 values. That's the first step in Krauts method. The second step is to use your U matrix. And this time we're solving for x1 and x2. So notice we went forward substitution for the first step and we used back substitution for the second step. And this is using our values from y1 and y2. So using back substitution, x2 is going to be equal to, we're going to divide 14 over 3 by 7 over 3. So that's 3 over 7 times 14 over 3. So 7 and 14, so that's 2. Okay, oh, I don't know why I've underlined that, a bit premature. And x1, okay, so the coefficient of x1 is 3, so I'm going to be dividing by 3. I'm going to have 17 minus 4 times whatever x2 is. Okay, so that's going to be 8. So 17 minus 8 is 9, divided by 3 is 3, and we get our solution. Okay, so if I was to change, let's say I was to change the right-hand side, I wouldn't have to change L and U. Okay, I just have to go through these two steps again to solve for x1 and x2. Okay. Does that did that make sense? Okay, I'll leave that on screen for you to be able to note down. Okay. What I recommend is, well, obviously there's a load of videos to watch. So there's videos on LU factorization, something called Cholesky decomposition, which for some reason I hadn't linked to it in Moodle yet, but I changed that, and also something called QR decomposition. So those are the three methods we're going to be looking at today. Isn't times 2 7/3 instead of 3/7? Do you mean in this bit? Yeah, we were dividing by 7/3. So excuse me. So to divide 7/3, I just inverted the matrix. As in matrix, inverted the fraction. Yeah. Okay. Right. Yeah. So we'll be doing more of these in the sessions on Thursday and Friday as well. Yeah. So are there any questions regarding LU decomposition? Can you, just a general question about the presentation, are you able to see what I've got on screen okay? Is that better than using a document camera? Because I had a bit of problem last week with it focusing and my hand getting in the way. Yeah. Okay, but it's better. That's good news. Okay, I think pretty much time's up there for this session. Okay, continue to work on the assignment. So continue to crack on. I don't mind if you send me questions about the assignment. Within reason, I will try and sort of point you in the right direction without trying to give the game away. What I would say is if you are really struggling, to do this 3-part A, what I would suggest is if you can get a set of values which give you a fourth order method, use those for the remainder of the question. So there's no point you struggling on this first part and then not being able to do all of this question. Okay, so I will still award you marks if you do, for example, using your ERK method. If you find another method which may not necessarily have these same values, and you use that here, and you do all of this correctly, I'll still award you the 10 marks. Okay, so don't sort of get bogged down on something, get stuck on one part. Just move on if you really can't do it. And then you can always go back at a later date and just try and sort that out as well. Okay, so right, I'll see you guys on the sessions on Thursday then. Make sure I stop the recording to make sure. Yeah.